that are on the internet. We strongly encourage you to send your questions for the Q&A at first opportunity, and the address should be at the bottom monitor of the transmission. So send them in as you're able, so we can have airtime to take them on. So with that, Kathy?
Hello, good afternoon, everybody. It's my pleasure today to introduce today's seminar entitled Characterizing Spatially Inhomogeneous Non-Criteria Pollutants in Los Angeles Air Basin. Now, before I introduce the speaker, I'd like to give a few introductory comments to provide a little more context for the study you're going to hear about today. First, previous studies have found that health effects are associated with proximity to traffic and exposure to roadway pollutants. Now, this is really important because near roadways, especially near freeways, the pollutant levels are higher, and during the daytime, the pollutants go to background levels several hundred meters downwind of the freeway. Now, during certain conditions, particularly those you might find during the pre-sunrise period, so the early morning hours where you have stable atmosphere and strong temperature inversions, the impacts of the freeway could be quite large, as you'll hear about in the presentation today. Also, it's important to note that other sources besides freeways are important for exposure. So sources such as airports and high-emitting vehicles can also be important for pollutant levels in neighborhoods and for personal exposure as well. So in the current study, they take these findings a step further and look to better characterize these pollutant plumes and gradients from the freeways. Basically, what are the most important factors that are driving these early morning phenomena in particular? Second, they're also looking at different neighborhoods and pollutant levels in these neighborhoods and the factors that influence those as well. And third, what happens when source strength changes? So for example, if you have a freeway closure, or if you are in a community or neighborhood where there's a lot of high-emitting vehicles, how does that affect the pollutant levels in that immediate area? So with that, I'd like to introduce today's speaker, Dr. Suzanne Paulson. She's professor and vice chair of the Department of Atmospheric and Oceanic Sciences at the University of California, Los Angeles, and she's also director for the UCLA Center for Clean Air. Please help me welcome Suzanne.
Thank you for that very nice introduction, Kathleen. So before I start, I would like to emphasize that the person who really did a tremendous amount of this work and in many ways intellectually led it is Wanshik Choi, who's a postdoc who's been working with myself and Arthur Weiner at UCLA for coming up on the last 3 years. And he was also assisted by Meilu He, who was a postdoc in our group, and Kathleen Kazawa and Steve Mara, who make the mobile platform run and also contribute in numerous other ways. And this work obviously has been supported by the Air Resources Board. So I'm going to do a little bit of a general introduction, recognizing that most of you people know most of what I'm talking about, but potentially some people in the audience may not, in terms of health effects. And just a very brief mention of the methods and some about the background, and then get into what will be a actually fairly technical discussion of the factors that control freeway plumes and how big they are in the early morning. And we will see that the atmosphere doesn't make it all that easy to tease that out. But in the end, we will be able to do a great job at predicting them, actually. And then I'm going to show you some results where we've tried to address the problem that we have of making measurements in different places at different times and wanting to compare them. And finally, give you some quick results from various measurements that we've been making over several years in different areas, all in the Los Angeles area. So in terms of health effects, as Kathleen mentioned, living near roadway seems to be problematic for human health with a kind of wide range of potential health outcomes. And all of these studies, because of the absence of criteria pollutant measurements that are good indicators of freeway pollution, instead of using a pollutant metric, used proximity to the freeway. And so while we have some insights into what might be causing that, it's certainly far from settled what it is about freeway pollution that creates health effects. It does seem to be clear that living near freeway is not good for you, and there are effects in terms of increased mortality. A variety of studies have shown increases in cardiovascular outcomes, including heart attacks and strokes, and also for adults a variety of other outcomes like increases of diabetes and asthma and respiratory symptoms. Children and including unborn children also seem to be quite significantly impacted by exposure to freeway pollution, and there have been several studies in Southern California actually, and also other ones in other locations around the world, but the ones that I picked are from my coworkers and people across town. Beata Ritz and coworkers at UCLA have shown associations between living near freeways, especially those with a lot of heavy-duty truck traffic, with increased outcomes of premature delivery and low birth weight babies. And then the fairly well-known Southern California Children's Health Study that was conducted largely at USC over a number of years had a number of outcomes that were associated with proximity to freeways, including increased levels of asthma, as you would expect, but also irreversible effects on overall lung development as children grow and then eventually reach adulthood. As probably most people in the audience know, but just to remind you, particles in the atmosphere come in many different sizes, and different sizes tend to have different sources. And this is really a cartoon from the 1970s, but it shows actually a lot of information. But if you look at the area under the white curves, you see what you would typically find in terms of particle size distributions in urban air away from a strong source of combustion particles like a freeway. And so you see fine particles that were mostly formed either emitted as smaller particles and grew to be in this size range, or they are actually the result of oxidation reactions of volatile organic compounds and also inorganic gases that have become more oxidized and become less volatile and condensed into the aerosol phase. So the fine particles are mostly formed in the atmosphere or formed by some kind of gas phase process. And then the coarse motor particles, of course, are formed largely from mechanical processes, cars driving over freeways, wind-blown dust, a lot of the sea salt aerosol, which isn't present everywhere but is present to some degree in LA, is also found in the coarse particles. The area under the blue curves are what you see when you are close to a freeway or really it's a freeway, but if you're close to a combustion source, you would also see these very small particles. Around freeways, you also see an enhancement of the coarse mode. That's the result of basically cars moving over the surface and also brake dust and so on. So the ultrafine particles, as they're called, these very little guys, are very substantially enhanced very close to combustion sources, and they also they really go away. They don't disappear, of course. What happens is they coagulate with each other or collide with larger particles and become incorporated in the fine mode. But in terms of making measurements, if you want to have a really good metric of where that freeway pollution is, the ultrafine particles are a great metric because the background is so low and the signal is so strong from fresh emissions from vehicles and other combustion sources. So this is a picture over here of the wonderful mobile platform, which is owned/leased and operated by and maintained by the Air Resources Board, and we are fortunate to get to use it sometimes and drive it around. And it has a bunch of state-of-the-art instruments inside. A lot of these instruments are relatively new, and the way in which they've really opened up this area of research is that they're fast. They're fast enough to get meaningful data as you drive around at normal vehicle speed. So the best of them have 1-second time resolution. Some of them have a little bit less. The main instruments that I'll show you data from are the condensation particle counter and the fast mobility particle sizer. These give us our measurements of ultrafine particles. Fast mobility particle sizer actually goes up to 500 nanometers or 560, so it goes a little bit above the ultrafine mode, but most of the numbers will be dominated by the little particles. And also, both of these instruments give you particle number, and a lot of what I'll show you will be particle number. We also have dust tracks that measure PM10 and PM2.5, a number of gas phase measurements, including particle-bound polyaromatic hydrocarbons. And we know where we are with GPS, and we also have some idea of what's going on in terms of vehicles going by with video records as well as human observers that are recording audio as we're driving around, actually. And then we also have a little bit of data from our tethered balloon. This is a temperature anemometer that we fly on a balloon where we can find space to do that, which I'll mention a little bit more about that. Okay, so freeway plumes in the early morning. So we've made measurements at all of the white dots as part of this study. And there were earlier measurements that I'll talk about. There was one right next to UCLA in 2001 and also in 2005. And then there's an earlier study that we also did with the mobile platform and many of the same players that took place in 2008. So I'll compare some, show you some data from both of those as well. But the other sites, there's downtown LA site, very much fairly close to the urban center. Another site that's down in the coastal plain, although it's a little bit complicated by this peninsula, and also this one's kind of in the coastal plain. The Claremont site is in an inland valley, so it's quite different. It's still somewhat influenced by the fact that it's fairly close to the coast, but it's really much different meteorology from the other sites. So in 2008, we made a bunch of measurements in Santa Monica, and we found the presence of the very large plumes in the early morning. And I must say that I completely expected when we went out to make these measurements that we would see a much bigger plume in the early morning because the atmosphere is so much more stable. But I was really astonished at how much bigger the plume is. So this shows the green line in the middle are earlier measurements that were made right by UCLA by Yifeng Zhu and coworkers. And those measurements show a pretty narrow plume that is decayed a lot by 100 or 200 meters away from the freeway during daytime. And these results have been reproduced by many people at many locations. And certainly the width varies somewhat, but it's within a few hundred meters that you get fairly close to background during daytime. In the early morning, we see this giant plume on the downwind side that goes out to beyond a couple of kilometers and a fair amount on the upwind side. This, as Kathleen indicated, is in a nutshell the result of the very stable atmosphere that happens in the nighttime. And as the sun sets, the ground surface cools. It cools the air right above it. It does not cool so effectively the air above that. So we have a situation of warm air above cold air, so a very stable layer right next to the surface. And as the night goes on, the stable layer gets a little bit thicker. Once the sun rises and starts to warm up the surface, we start to break that down. Although we'll see that the effects of having trapped a bunch of pollution from the morning rush hour will last through the morning. to some degree. So if I show you, the last data I showed you were all normalized to the peak concentration. So these are the absolute numbers for Santa Monica. And the red line is the winter. Actually, that was in March. And the blue line is for the summer. It's in late June and early July. Much lower concentrations in the summer. This is not for the reasons that probably pop into most people's heads. When I ask that question, people will typically guess the wrong thing. It's not because there's less traffic in the summertime, because kids are out of school and on vacation or something. There is a little bit less traffic in the summertime, but just a little bit. So this shows the green is the summer and the red and pink is the wintertime, more or less the same. And it's also not because there's more mixing in the summertime. The nighttime stable layers happen all year round on clear nights. They're extremely common. They don't happen everywhere every night, but they do happen most places, many nights, all around the globe. It's not as though this is a unique situation just for Santa Monica. Although there are little details that tend to be unique to each particular meteorological or geographical situation. But the real reason that the concentrations are much lower in the summertime in our measurements is that in both cases we measured for an hour and a half or so before sunrise and a half an hour a little more after sunrise, but the sunrise is a lot earlier in the summertime. And so we were interacting with a much smaller amount of traffic in the summertime than we were in the wintertime. In the wintertime, the sunrise is later, so more of that morning rush hour gets trapped in that early morning air. And it's not, we were measuring earlier, but if we measured later, we wouldn't see as big of a plume because when sun rises, that plume starts to collapse. So the concentrations will be lower as a result of this phenomenon in the summertime than they are in the wintertime because of when the sun rises relative to when the morning rush hour is. So, potentially we could just keep our clock so that the sunrise is always very early, and then we would actually potentially have some health benefits from that. So the factors controlling freeway plumes in the early morning and also whether or not we could reproduce those results in other locations were the focus of the study that I'm reporting on now. And so we went and made measurements at 4 other locations. We expected to find, kind of the same thing, and we did find kind of the same thing, but not exactly, and we learned a whole lot more about how this works, for sure. One of the things we found is that we didn't really reproduce that upwind part, and actually the curves are much more regular looking in the current study, and that is basically because we kind of averaged some data that we shouldn't have averaged together that had different sampling lengths earlier. So those sort of weird shapes are somewhat of an artifact of something that we didn't do quite right. So we have less upwind, and we have, in the downwind side, you see that the curves actually, especially this red curve, but all of them pretty much do this, they don't really ever go back to background. They stay pretty much elevated downwind until who knows when. Eventually we get into a situation where there's a big cross street or another freeway, and we just can't get meaningful data once we get into that situation. So we can't measure forever downwind. But we see very clearly that it levels out to an elevated level. You also notice if you look at that peak, that the peak is not always in the same place. And that is because 2 of our sites they had different geometries. 2 of our sites, the freeway was going over the road that we were making measurements on, and 2 of the sites we actually drove over the freeway. So it was right underneath us. And so those are overpass freeways, so the freeway is overpassing us, and underpass freeways. I'll warn you that for the next several slides, things will get potentially a little bit confusing. So I'll do my best to get through it, but and kind of remind you. And also if you zone out or whatever, we'll come back to much easier stuff and stuff that's not related to this, so you can tune back in. So yeah, I always tell my students to never put an equation on a slide with more than about 3 terms, and here we are. It's one of the first times I've done it, but I couldn't figure out another way around it. So we looked at our freeway plumes, and we tried several different models to try and fit the shapes of those curves. And the model that did the best was the original one, actually. It's a Briggs formulation of the Gaussian plume dispersion model. And we could get the best fits with this model. And this one basically has, it's a fairly simple expression. Concentration is over here as a function of distance from the freeway and distance above the ground surface. And it is Q sub C is related to the emission rate, which is correlated with wind speeds and traffic speeds. And then there's this dispersion coefficient sigma Z, which appears 3 times. And then this double exponential that is just a function of H is the height of the freeway above or below where you're measuring, and H is where you're measuring. So it's a fairly simple expression. In the Briggs formulation, there are stability classes that give you values of alpha and beta that are the adjustable parameters that determine the dispersion parameter sigma Z. And I'm going to talk a lot about QC, alpha, and beta. But for stability classes, there are only a couple of classes for very stable cases of the early morning. There are several more for daytime, but we're not interested in that. So basically, using what's in the literature, we have no predictability because there's just kind of one number for all of our conditions. So that's not going to help us very much. And for urban areas, we do expect less dispersion for the same wind speeds because of the the buildings that basically get in the way of the dispersion. So this model works really, really well. These are its fits to data. The total average data, we have about 4 or 5 days for each of these sites, and for each of those 4 or 5 days, we'll drive up and down this transect that is 3 or 4 kilometers long, maybe 3, 4, 5 times, depending. So we have 20-ish transects for each one of these, and we average them together. The gray is the total range of the data. The squares are the median. Oops, and the red line is the fit. And the fits have correlation coefficients that are all above 0.9. Some of them are 0.96, so that it really fits it really, really well. And then from this, so we get the best fit, and then we can figure out what QC, what alpha, and what beta fit that curve. So for QC, we can, QC is very closely related to the particle emission factor for the vehicles, and we have the amount of vehicles on the freeway because there's this wonderful network of sensors in freeways, something like every mile, measuring freeway traffic. So, so Q sub C is just equal to the particle number emission factors. We're doing numbers here. In numbers per mile per vehicle times the traffic flow divided by basically the square root of the wind speed. And, the wind speed. So we can just rearrange that expression and get Q vehicles and put in our number of vehicles for our different sites. And overall, for all of those 4 sites, which are some mix of mostly gasoline vehicles, but also some trucks, we get a final value of 1.2 times 10 to the 14th particles per mile per vehicle. And we can compare that number to the number that my colleague Yifang Zhu and coworkers derived for their measurements in 2001 in West LA, and our number is only about 15% of their number. Now, there are error bars on both numbers for sure, but clearly there has been a really significant drop in ultrafine particles during that period, even though ultrafine particles were not a target of any specific regulations. Okay, so that's QC, and when we get out of that, now we have to do the dispersion coefficients alpha and beta. So this is a little sensitivity study for alpha and beta, and The top plot shows what happens if you hold beta constant and you change alpha. And basically, if you look at it, you notice that if you change alpha, the peak moves over, or the peak changes as alpha decreases, the peak moves over. And it also kind of looks as though the plume decays not as rapidly. But alpha is very sensitive to where the peak location is. And beta doesn't care at all about where the peak location is. Beta is really the part of the term that is related to plume dissipation. So as beta decreases, the plume goes away more rapidly. So now we're going to look at how alpha and beta are related to each other, and also how alpha and beta are related to things like wind speed and wind direction, and things are about to get kind of confusing, unfortunately, because they're basically, the early morning, the wind speeds are very low, and and it's all kind of stable, so there are multiple things making both of these factors go in different directions, and sometimes it's really something else that's controlling the factor rather than, it's sort of an indirect effect. So there are strong positive relationships between alpha and beta, but the data clearly segregate into two groups, the underpass group and the overpass group. So the geometry of that intersection has a lot to do with how the plume decays and what shape it has. So interestingly, for a situation of more dissipation, so low beta is associated with more transport. So that's not entirely what you would expect. So the peak, if there's more dissipation, the peaks tends to move over, but changing beta by itself, alpha by itself that way, moving the peak over results in a slower decay. So there's a little bit of a sort of counterintuitive aspect there. So, but getting back to the freeway geometry, if we drive over the freeway versus under the freeway, we see different things in our plume shape. And obviously, if we drive over the freeway, then we're going to get our peak concentrations right when we're over it. So there's no issue of the wind moving the plume anywhere. But if we drive under the freeway, then the plume has to leave the freeway. It gets dispersed some or a little or a lot depending on the stability of the atmosphere, and eventually it reaches the ground. So there's a couple things going on there at the same time. It's getting moved, and it's also being sort of maintained or having a lot of entrainment and changing its concentration, and that sort of, those two things turn out to go kind of in the opposite directions. So in order to explain the relationships between alpha and beta and meteorological conditions, actually meteorological conditions couldn't explain all of the relationships with alpha and beta. Another really important part of how this works is the plume intensity, so how different the concentration is from the background. And if you think about it, if you have a plume that is, say, 100, and you have background that's 0, and you dilute it by 50%, you'll get, or you have a 1-to-1 dilution, you'll get a resulting plume that's 50. But if the background's 50, and you have a plume at 100, you do the same thing, you get a concentration that's 75, right? So the difference between the background concentration and the plume concentration has a big influence on how the plume decays. And this is also part of the reason that when you see our plume decays, they don't really go back to background. So the decay slows down a lot as you go on longer. And that's partly because as you go on longer, the plume becomes very similar to the background concentration. And so that it gets diluted more slowly and maintains itself for longer. Okay, so this is the relationship between alpha and wind direction. So here, 90 degrees is perpendicular to the freeway, and a lower value of alpha means more transport. So this does exactly what you would expect it to do. If the wind is perpendicular to the freeway, the plume gets pushed further downwind than if the wind is more or less parallel to the freeway, right? So that's all, everything's that seems to make sense. The data are kind of scattered, so it's not a super strong relationship. This is a relationship with wind speed. It's a little complicated, and the trends are not that strong. So there are actually two forms of the wind speed that are plotted here. The one on the left is the resultant wind speed, so that's the net wind speed in perpendicular to the freeway, so in a particular direction. The one on the right is the average wind speed, so the average wind speed in all directions. So the one on the left is more of a transport-related thing, and the one on the right is more, you would expect it to be more related to turbulence and mixing and entrainment. There is somewhat of a relationship in some cases to the transport term alpha for the resultant wind speed, and at least the overfast freeways do what you would expect, and sort of, and that is to have more transport when the wind speed, the resultant wind speed is higher. The underpass freeways really don't have much of a trend except for that one point, and that one point actually the wind went from the other, it was not in the normal downwind direction, and there was also some fog, so there were other things going on that one point. And then the scalar wind speed is sort of related to the, you sort of see more dispersion when you have more scalar wind speed, although you don't see, certainly not a very strong relationship for the overpass freeways. And that is probably because of this problem that a higher wind speed you would expect to transport the plume further. This is where the freeway is above you. But a higher wind speed would also be associated with more mixing. And so that will result in lower concentrations. I'll just leave it at that. So the effect of plume intensity is really is quite strong. And if we look at the relationship between plume intensity and beta, we have a very understandable relationship. So as the plume intensity becomes larger, over at this end, then we have more dispersion. So beta goes down, and we have more dispersion. So, so if we have a very big peak relative to the background, it looks as though it's being dispersed more rapidly if it's bigger. So it's not that there's necessarily more entrainment, but the peak goes away more rapidly because of the effect of the high concentration relative to the background. There's also quite a strong correlation between alpha and plume intensity, and this one is not exactly what you would think should be there, because you have a situation where, first of all, it's not even that clear how plume intensity should be related to transport, and then also when you have more intense plumes, you have more transport. But the way that we rationalize this is that actually what more plume intensity means is that you have a more stable atmosphere. So in that case, you have the plume, especially for the overpass freeways, is more constrained because there's less entrainment, so it stays tighter. And also, if you have a more stable atmosphere, you tend to have lower wind speeds, so it gets transported more slowly, and it takes longer for it to reach your measuring site at the ground. So we have this kind of counterintuitive effect, but it's a very strong relationship. But it's really sort of something else that's controlling the effect, the relationship between plume intensity and alpha. It's not a direct effect. This is the relationship between the atmospheric stability. So this is data that we got with our tether sonde, and it turns out that there are lots of rules about flying balloons in urban areas. and actually, it's not really that clear how you should interpret them. And you could probably and nobody really, I mean, even the people who should know aren't really that clear on it. And so it kind of comes down to, we find a place where we think we can do it, and then we see if we get yelled at. And if we get yelled at, then we don't want to get in too many fights, so we just kind of give up. But it may be as bad as you can't be within 5 miles of an airport, and there are a lot of airports in LA, little ones that you wouldn't really notice. But you also need to be in an open field where there aren't a bunch of wires and buildings that you can run your, because the thing is blowing at least a little bit. And so as you can see, for Carson, we only got one measurement. The other ones, we only got a few measurements. So we don't have quite a complete data set for this. So, but what's plotted here is the Richardson number, which is meant to be really kind of a qualitative metric of the atmospheric stability. And it's not really maybe exactly right to expect even a quantitative relationship, but we just put these little eye guide lines in there. All of our measurements are positive, so they're all in the neutral to stable range. Some of them are more stable than others. And we do see that there seems to be more background concentration when the atmosphere is more stable, as you would expect. There also, curiously, seems to be more dispersion, so under more stable conditions. This is another one of these kind of counterintuitive results. And we think that really what that is that under more stable conditions, the plume intensity is larger. So we get more concentrated plumes, and those things have higher dispersion because they dissipate rapidly because they're so much larger relative to the background. So that's really this plume intensity effect showing up again and screwing up how you think the world should work. So there we are. I mean, this is what, this is the data, and this is what nature tells us. Or at least that's the best explanation that we can come up with to explain why that relationship is what it is. Okay, so we did all that to try and understand what's controlling the dispersion. And then we decided that we wanted to figure out if we could actually calculate our plumes from measurement data, from data that you could conceivably just go out and measure directly. And so if you have data of Q sub C, the emission rate factor, which is just a function of the emission per vehicle per mile, so you could put in whatever number for that actually, as long as if you want to do it compared to different places. It just becomes a relative number, and the wind speed. So that's just really dependent on the wind speed and the traffic speed and whatever you have for the emission rate. And then you have wind direction and wind speed. Yeah, wind direction and wind speed. Where is that cursor? So wind direction and resultant wind speed and the temperature and the relative humidity, then you can, which is pretty basic data, basically just the Met data, then we can do a multivariate regression and calculate Q sub C, alpha, and beta. And once you calculate those, then you can just plug those into the dispersion equation and get your plume decay. So, so we're happy to report that actually we can calculate alpha, beta, and Q sub C very, very nicely given just these data. So we use our multivariate regression and then recalculate them, and we can go back and repredict the plume shapes very nicely. Okay, so that's what I have to say about the factors controlling the plume shape. Not that simple to explain, but we can definitely predict it if we want to. And this is just a graphic that kind of summarizes the exposure of people who live along freeways, roughly. So this is a typical daytime 200-meter exposure area on the normal daytime downwind side, the green area. And then on the normal nighttime downwind side, which in Los Angeles typically are orthogonal to each other. This is not true everywhere, but in Los Angeles we have this sea breeze, land breeze system that happens most days. So there are many more people exposed at night. The concentrations also tend to be significantly higher at night. So it's a large swath of people living on the downwind side at night who are most affected. So in LA, something around half the population lives within 1.5 kilometers of a freeway. So not all of them are on the downwind side, but there'll be 25 or 30% of the population will be directly exposed on one side or the other. In the United States, 11% of all households are apparently located within 100 meters of 4-lane highways and roadways. So the pre-sunrise freeway and early morning freeway plume potentially has more impact overall compared to the daytime due to both its higher concentrations and the much larger area of people who are exposed. Okay, so on to a different topic. If you zoned out on the last one, you could consider tuning back in. So this is a discussion of classifying days based on their meteorology and looking at whether or not we can predict based on meteorology what primary pollutant concentrations should be. So in the 70s and the 80s, some of this was done for secondary pollutants for ozone. And obviously, if you have ozone, then you need to involve things like the amount of sunlight. So you involve different factors. So this is an analysis just for primary pollutants that basically completely ignores photochemistry. So this is because we have this problem that we have all this nice mobile platform data. It's data that, those vehicles are very expensive. We don't have lots of them. We can't drive them in different locations. So we can only be at one place at one time. Maybe you've experienced this problem yourself in your life. But we'd like to be able to compare the results. So we've put together this classification system. So we could do that with like an airshed model, but then you would still have to figure out how you're going to classify the days and exactly how you're going to deal with this statistically. So we just did a pretty simple, straightforward statistical analysis where we got all of the data that we thought would be important and plug that into our basically multivariate regression scheme. And that includes upper air data for various aspects of meteorology that comes from the NSEP model. So it's data that's interpolated and then we have surface observations from LAX. And that includes pressure at different heights and temperatures in the upper atmosphere. A lot of them have to do with the thickness of the mixed layer around the LA basin, and then lots of surface meteorology. So then we take all the data in this nice statistical program that actually has been used for an amazing array of different applications that have nothing to do with atmospheric science as well as atmospheric science. Goes through and bins the days based on cutoff points. And here we're doing it for the maximum carbon monoxide concentration measured at the downtown Los Angeles AQMD station. And it divides up the data into, in this case, 11 nodes. And if we look down at the bottom, so the breaking points are here. So the first one is based on wind speed. Was it a really windy day or not? That's, if you've been in Los Angeles at all, we have some incredibly windy days, and most days are not very windy at all. So that's kind of an obvious thing. And then we have the pressure at 925 millibars. We have the north-south pressure gradient. This turns out to be related to whether or not we have Santa Ana winds or how strong they are, and then some temperature issues and stuff. And these things break out the days into various bins. the final breakpoints are down in the tops of these boxes. And then we have the average carbon monoxide concentration for each of the bins. So they vary from 0.55 all the way up to 2.3 parts per million. And the standard deviation, and then n is the number of days in each bin. Some days are more common than others. So you notice that it's split up pretty well, but actually for a lot of these bins, we can't really tell. These two should have pretty much the same carbon monoxide, but even comparing, say, this one and this one, the standard deviations, these are only 1 sigma, are pretty large. So, so we can't do very fine splitting, but we can at least do some kind of larger scale splitting. It turns out that the classification system works really, really well, except that the error bars are larger than we would like. It would be more useful if they were smaller. But this shows daily CO max versus daily NO max and daily NO mean. And we see these very nice linear correlations in all of these cases for the different bins. So it seems to be very well behaved between pollutants and between different metrics, like the daily mean NO and the daily max NO and the daily max CO. This shows the same, this shows the relationship of the mean nodal carbon monoxide maximum for a bunch of different stations, Long Beach, Pomona, Ruby Doo, San Bernardino, and Upland, versus the downtown station. And for stations that are in a similar kind of situation geographically, the coastal sites and Pomona, which is fairly close to downtown LA, have very nice one-to-one relationships. When we start to get a little bit further away to the more inland valleys, we get a little bit, the relationships are still generally quite linear, but they have a little bit different slope. There is this one pesky node, node 2, and that node is strong Santa Ana node, and that's where the winds come from completely different direction, and the winds tend to be extremely strong near the mountains. Anybody who's lived down there sometimes will have stories about their trash cans arriving at a couple blocks away, but they fan out over the coastal plain near the ocean, so it has much less of an effect on the wind speed, so it makes the different parts of the LA Basin look very different under that one particular classification. So we're going to use that to compare our data from different days. So this is actually not, this is going back to some of the earlier stuff that I have, and then I'll get back to the cart analysis in a second. So this shows data for neighborhoods in 2008, a bunch of neighborhoods that we drove through. So this is just residential areas. There is some driving on freeways and major arterials, but this is just looking at the residential area data. And this shows ultrafine particle concentrations as a function of time of day in different seasons in West LA and in downtown LA, and it shows some interesting things. So in West LA, which I talked about when I talked about the pre-sunrise data, we have high values in the morning. So this is not the early morning. This is like 9 to 11 in the morning. We have high values in the morning and significant decreases throughout the day, and then same thing in the summer, but they start from a lower value. So this is the effect of the sunrise happening earlier in the summer and clearing and basically allowing less of that morning rush hour to get trapped in the air, and that sort of persisting throughout the day. When we go to downtown LA, we see a completely different relationship. We actually have lower concentrations in the morning, in the springtime, in downtown LA and Boyle Heights than we do in West LA. But in the afternoons, they go up. And that also happens in the summer. And we believe that is actually, and we're not the first people to suggest this, and certainly the metrics that we have are not probably the ones you would exactly pick to study this exact phenomenon, but our data are completely consistent with there being a fair amount of actual nucleation of fresh particles in the downtown area. So we have higher ultrafine particles in the afternoons in the downtown area, but we have lower black carbon because there's more mixing. There's certainly plenty of trucks driving around and stuff, but there's more mixing in the afternoon. And there's also lower NO. So to some degree, the black carbon, the ultrafine particles, and the NO all come from the same source. At least in 2008, there were plenty of diesel vehicles that were producing all three, and then there were also some gasoline vehicles that were producing some of them, but maybe a little bit more of this. But the one source that produces ultrafine particles, but not the other things, is fresh nucleation of fresh particles. So all of our data are consistent with actual nucleation of, there is a result of photochemical oxidation of organics and NOx producing fresh particles in downtown. So, okay, so I'm now going to show you some afternoon data for several locations, and it's all summertime data. And there are some measurements made in 2008 and others in 2011, and some in downtown, some in most of it in West LA. And there are over on the right, there's the final node of CART that these days fall in. So what was their meteorology? So all of them fall into node 2, except for a couple of the highlighted columns. And this, by the way, is a summer-only classification. So we get a little bit finer splitting for the summer only, but it's a little bit better than if we do the whole year, but it's still not really, really great. But the 2 days that did not fall in the node 2, which is the cleanest day, people always go make measurements on the cleanest days, right? I don't know why that happens. Were this one day in 2008, and that fell in node 5, which should have been somewhat higher concentrations, and the other one fell in node 1, which also should have had higher concentrations. Now it turns out that this day had pretty much the same concentrations as all the other days, so we did average it in with the other data. This other day, incredibly inconveniently, happened to be the Carmageddon day, the day when the 405 freeway was closed, the one special day when we really wanted to get data and compare to all other days. But as it happens, it should have been dirtier. And you can keep that in mind as I show you what actually happened. Well, you can see right there, it certainly was not dirtier. This is the bar on the lower right-hand side is the day when the 405 was closed. This is ultrafine particle number concentration. It's getting really close to our detection limits. Really, really, really low. And this is not right next to the freeway. In fact, it's upwind of where the closure was. It's in neighborhoods that were within a few miles of where the closure began, and then several more miles to the end of it, and on the upwind side. So as it happened, when Carmageddon happened, hardly anybody drove anywhere. I went out and drove places, and it was a wonderful day. It was just incredible how you could just go anywhere, and there was no traffic, hardly any traffic anywhere. When the 405 was closed again the next year with basically the same phenomenon, everybody remembered that, and it was a normal day with lots of traffic. So it only happened once, and then everybody learned Peter could only cry wolf once. So looking at the rest of the data, we see, this is afternoon data, we see much higher concentrations in Boyle Heights and downtown. Part of that is due to higher incidences of high emitters and so on, but it's also partly due to this, we believe, nucleation of fresh particles. If you look at the 2008 West LA data versus 2011, you see a pretty significant drop. And this is just a few days. It's not as quantitative as the other value, but so it's consistent with ultrafine particles dropping a lot. So yeah, actually just you may be thinking, well, what was happening with the car and the truck traffic during those days? And if you set this one to 0, cars were slightly higher on that day. but very similar. But by 2011, there was actually a drop-off in the number of trucks on the 4 or 5 freeways. But the truck levels were very low to begin with, so it's not responsible for that. It can't be responsible, or it shouldn't be responsible for much of that drop, because it was still, it began at like, I don't know, 3% or something, and went down somewhat from there. On the Carmageddon day, the traffic on the freeway nearby went down by 60% relative to this day, but not relative to, well, I guess also relative to this day. And the trucks were down 82% relative to this as a control, but only down a little bit because there were hardly any of them to begin with. If we look at PM 2.5, we see basically no discernible effect. These are not enough days to take these differences seriously. So no discernible effect in this data anyway, except during Carmageddon, where we had a really large drop, like 70 or 80%, which is much more than there should have been. The vehicle, removing the vehicle part of the inventory shouldn't have reduced it more than at the outside maybe 35 or 40%, but the drop was significantly larger than that. And we also see sort of the same thing, but a more damped effect on NOx. Although we note that these guys could be, NOx is probably titrated somewhat by ozone in downtown area compared to West LA, where the ozone levels are lower because we have less photochemical oxidants and secondary organic aerosols and so on, because we're so close to the coast. Okay. Now just a few slides on neighborhoods, some inter-neighborhood measurements in West LA. So we have divided up our areas around the 40510 interchange into 4 neighborhoods. This one called SMA is downwind of Santa Monica Airport under typical wind conditions, which is drawn here. So basically that airport is perfectly lined up to be lie exactly on the average wind direction in that area. And the aircraft pretty much always take off from the the east end towards and fly to the west into the wind. And then we have A, which is upwind of both freeways, B, which is downwind of the 10 freeway, and C, which is downwind of both freeways under typical wind conditions when we were making measurements. And you see pretty much what you would expect. You see higher concentrations in C than B than A in most of the data. And then you see these really high concentrations at Santa Monica Airport. And if you notice, there's a break in the scale there. So actually the averages, which are the red dots, are above 100,000 for the Santa Monica Airport. The median is quite a bit below that, but the averages are way up there. So a lot of variation between the different neighborhoods. So that's pretty much the data that I have to show. Just to recap a little bit, just a couple pages of summaries. For the pre-sunrise plumes, they are very large compared to daytime plumes, and that's a general result that we could reproduce all over Southern California. We expect we could reproduce it lots of other places if we could drive our mobile platform further than it will go based on its battery range. The Gaussian dispersion model allowed us to extract a particle emission factor and dispersion parameters, and fits the plume actually very nicely. And plume intensity is a surprisingly important factor controlling plume length downwind of freeways, but also wind speeds and directions and atmospheric stability are important. Based on the strong correlations of dispersion coefficients, we can predict plume shapes and area impacts. In terms of neighborhoods, the regression tree analysis is helpful, but it would be great if it provided more resolution than we could get out of it. But it's a helpful and quite straightforward technique to use. UFP are much more variable than other metrics like PM and NOx, as we would expect. And overall, the behavior of ultrafine particles as a tracer of mostly as a tracer of freeway pollution, we can always explain them with pretty simple explanations, but they're fairly complex, and so they're certainly easier to explain than they are to predict. And that's what I have to say.
I think we'll start with a question from the web, if that's okay. I'm just going to give it to you, and
Okay.
you can go ahead and...
So the question is, why is there more nucleation in downtown LA? So that's a great question, and I'm sorry I should have explained a little bit more about that. Actually, it was surprising to me, and I think surprising to other people, that there is nucleation in downtown LA, because there's a large background concentration already of particles, and you might think that condensing species would have enough particles to stick to without going off and nucleating their own fresh particles. But in fact, it seems that they do. But in West Los Angeles, we have the situation where we have the coast, and the freeway there is 3 or 4, maybe 5 kilometers from the coast. So we basically have reasonably clean air that has usually been going over the ocean at least for a while. Actually, interestingly, often, if you go back 24 hours or more, it has come from the Central Valley or from somewhere up on the coast and then gone along over the ocean and comes into LA at that area. But it's relatively clean, and then we add a bunch of pollution to it, and then it takes time for photochemistry to happen. So there really isn't time once you get to just a few kilometers from the freeway, plus there hasn't been that much emissions yet. And then as the wind carries the air mass further inland, there's more time for reactions and more pollutants to do reactions, and so eventually you would expect that you potentially get nucleation. It's a bit surprising that it's already happening in downtown LA, but that seems to be what the data says. So, yeah.
Sam Punazeri from ARB, from PTSD division. My question is basically on your, from the point, I have a couple of questions, but I try to summarize them in one. So when you start with your dispersion model, you first are talking about your sigma z formulation from Briggs equation. Basically, that equation is 1 plus beta x to the power of half. That's not 1 plus beta x. For urban condition, that's 1 plus beta x to the power of half. And that's why that when you put the alpha and beta for the urban condition into that equation, you basically will see that your dispersion is enhanced. Because if you look into the literature over the past 20 years, you can see the micrometeorology in the urban dispersion condition, under urban condition, although wind speeds are lower, but usually turbulence levels are higher because of the presence of roughness elements in the urban conditions. So, so that will start, that'll start my question basically like, first of all, the Briggs equation is like a 30 years old, 40 years old equation. There are a lot of literatures on the relation of the micrometeorology dispersion over the last 20 years, which you can use the friction velocity or boundary layer heights to relate the sigma z to these micrometeorology. And then my major question is basically, how come, dispersion is all about atmospheric turbulence. How come we relate dispersion, the atmospheric turbulence, to plume intensity or wind directions or relative humidity or basically what I can see from your regression equations is absolute temperatures. And it doesn't, what is the physical meanings of these variables under dispersion parameters? Thank you.
Well, so there's been a lot of work done in the last 20 or 30 years on this sort of thing. Almost all of it has been done during daytime. There's not much done in the early morning. And so I think that we need to think about it in a different way, where there's really very little turbulence. The wind speeds are very low. And so the processes are kind of different. So So certainly, you know, the effect of relative humidity, for example, is indirect. The reality is that empirically it fits the data. And it contributes to giving us a better regression. And the same can be, I mean, you know, obviously when I talked about wind speed is, you know, there's a lot of things going on with wind speed. So there are a lot of very indirect relationships there. And again, you know, when we talk about this stuff, often people might bring up the question about what about the heating from the road surface, but there's no heating from the road surface when the sun's not up. It's, you know, so there are processes that are going on in the early morning that are, well, there are actually lack of processes in the early morning that make it a really different regime.
Yeah, but my main question is that when you're developing your regression equations, I mean, at least for dispersion modeling, all your variables should have a physical meanings. I mean, you should basically base your regression model should be based on the physics of the problem. And how can you relate your physics of the problem, which is atmospheric turbulences? I mean, I can sort of agree with the with your highway, like, because your obstacles will change and that will change your turbulent intensities. But how can you relate your plume intensity as a variable that can do anything to the physics of the problem, which is dispersion?
It doesn't do anything to the physics, but it affects the plume shape tremendously. I mean, but maybe I should also say that it is a result of the physics to some degree, because when you have a more stable environment, you tend to have higher delta C.
Yeah, but dispersion is all about turbulence. It's not.
No, that's right. That's right.
It's not a monster.
But it's a, yeah. But it. So it's a, you know, we can't measure the turbulence, or at least we didn't measure the turbulence, and that's not something that is very easy to measure. So we wanted to try and figure out whether or not you could predict the plume shapes based on things that you could actually measure without really fancy equipment. Okay. To what extent are these results relevant at other locations throughout the United States? So this is a really interesting question that I wish I had a really quantitative answer to. And maybe that's a question for further study. But I think it's fairly easy. It would be fairly easy to figure the answer out, in, even reasonably quantitatively, based on our relations with wind speed and stability and other factors that seem to control the size of the plumes. So that's sort of from a quantitative perspective. But again, as I said before, nocturnal surface inversions are kind of the canonical thing that happens at night. And so they should be very common in many places, except places that are, you know, very stormy and very windy, or have, I don't know, various kinds of geographical arrangement of things that might result in some other kind of situation at night. But basically, most places where it's a clear night, you get a nocturnal surface inversion. So with typically low wind speeds. Oh.
Hi, Suzanne Bart-Cruz with the Air Resources Board. Thank you for a very nice talk. Covered a wide range of topics. I had a question on slide 18 where you showed this 85% reduction in ultrafine particle emissions per vehicle per mile over about a 10-year period. So I had two questions. One is directionally that's consistent with what we expect to be the effect of the diesel particle filters that were implemented over that time period. That in our laboratory we've seen, you know, a factor of 50 to 100%, 50 to 100 fold reduction in ultrafine particles, but I don't think we have corresponding measurements for gasoline fueled vehicles. So I had two questions. One was, is it possible to do this calculation for gasoline vehicle-dominated freeways versus diesel-dominated freeways, if you have the data to do that between these two time periods, like the 405 versus the 710? And then two, if you've looked at other pollutants like NOx or CO, where we actually have good data sets to compare what was observed on the freeway versus what we would have expected from our laboratory measurements.
Excellent questions. I think that we could do it for NOx. The trouble with the thing that makes it a bit difficult and would make it significantly more uncertain is that we get the Q sub C by fitting the dispersion equation. And while we see a plume decay for NOx, it's nowhere near as clear as it is for ultrafine particles. And so that means that the quality of our Q sub C values and the resulting emission factors would be significantly lower. So there would be significantly more, the result would be significantly more uncertain. And that's basically because the NOx plume is much, it's above background, but it's nowhere near as much above background as the ultrafine particles are. And then the other question is about the gasoline versus diesel-dominated vehicles. I don't know. We should look at our data and see if we can do that. I think since we were making measurements so early in the morning, and just because of the locations that we picked, and unfortunately, locations to do these studies are kind of hard to find because we need to find a transect with very little traffic of its own, especially if they're high-emitting vehicles, like in a lower-income neighborhood. So we can't kind of say, oh, we want to do a transect on the 710. I think we looked at the 710 and we just couldn't find anywhere where we could do one. So I don't know that there's that much difference in the traffic. There is some, but
I know Zoo
did
did measurements
on the 710.
In 2001 or 2002. So, and I think you're using her data for the 405. So
yeah, we are.
But you didn't revisit that same 710 location that she measured at.
Yeah, I don't know off the top of my head where that site is, but since she was making measurements during the daytime, she needed a much shorter segment. Okay. We need segments that are 3-4 kilometers long, which makes it really hard. But it's an excellent question, and I can look at the data a little bit more and see if we have enough difference between our sites.
Bob Sawyer, University of California at Berkeley. Professor Paulson, really nice collection of data there and analysis. The Claremont site, it seems really different in terms of never getting anywhere near to background. Is that just because you didn't get far enough downwind, or it was extremely stable, or what's going on there?
First of all, so that particular site has a very, very clean upwind area because it's basically the mountain foothills where almost no one lives. And overall, actually, if I showed you the absolute concentrations, is much cleaner than any of the other areas. So we get into a situation where on the downwind side, we get into LA. So some of the lack of decay of that plume may be because the background in the downwind area is higher than the background in the upwind area. So it just can't ever go back to that upper background level.
Thank you.
Yeah.
Marc Bessière, Air Resources Board. I was interested by your use of the CART analysis, and you seem like you're interested but a little bit disappointed. So what do you think could help you get better result from that? I was thinking, do you believe maybe a larger set of observation would provide more interesting trees, or possibly inclusion of maybe intensity of traffic information in your analysis?
That's an excellent question, and I don't really know what would make it better. There are a lot of confounding factors, like, we have measurements at a particular surface site, and actually, by the way, I didn't mention, but that data was, I believe it was either Monday through Thursday or Tuesday through Thursday. So we took out all the weekend data, and we took out, I believe we did take out Mondays as well, because there are a lot of Monday holidays. So we tried to kind of constrain that, and it's for a set of 3 years where the traffic data overall was not changing much, but it's still one location, and there can be variations there. And then there may be some meteorological variables that we really need. I'm not sure what they are, but there's some other factor that we don't really know what it is that's creating that relatively large standard deviation. So, in my dreams, it would have been something where I could have actually taken data for a given day and normalized it to the CART results. But I don't feel like the data are really quite. You could do that if you're doing summertime versus wintertime and have some confidence that you gain some insight, and and that you could do that justifiably. But for days that are fairly similar, and days, for example, all in the summertime where they all cluster in one part of that diagram, you can't really do that. So it's a great question.
And Walter Ham, AirB. I was curious in your modeling how you treated the surface, either as absorbing or reflecting, and also if you saw any evidence of coagulation events.
Absorbing or reflecting?
Reflecting particles up from the ground, or if they're just depositing onto the surface.
We completely ignored it. I don't know, we didn't do anything with the surface. And do we see, well,
coagulation events?
Actually, I should say, we have another project that we're working on right now, trying to look at the size distribution and see what we can get out of that data in terms of how much evaporation versus coagulation there is. And so the ground surface we will deal with in that paper, but it's not something that we have dealt with so far. Well, once we get those results out, it's hard to feel confident about those results. So that's work that's really still in progress. So yeah, but I can say that I'm not sure if I remember the numbers exactly. There is some stuff going on other than pure dilution in those plumes. And if you look at particular size bins, then you see that more than when you see that in for the particle distribution as a whole. It looks like there's some evaporation. Obviously, there's some coagulation. There's also an effect that is kind of. The fact is that we can fit the empirical data very nicely with that model. But if you think about it, we have this plume that goes out a couple of kilometers. The wind speeds are of order a meter a second or less in the early morning. That means that the air that's 2 kilometers down there was actually emitted by the freeway an hour earlier, when the traffic was different and lower. So that sort of complicates the analysis a little bit.
Dr. Paulson, it's a great talk. Steve Mara from ARB. I see on your last slide here that the concentrations in the Santa Monica, downwind of the Santa Monica airport were really very great. Are there plans to see how far those emissions go into the neighborhoods, or is that?
So our main tool to do that is the mobile platform. Can I say this? You guys don't really want us to look at airport emissions? I mean, it's not, yeah, just because it's not something you can control. Yeah, we haven't really looked at that in any great detail, and we don't have plans to do it. Particularly, I don't know, maybe if we're in that neighborhood one time, we'll, once in a while, we'll drive by it a few times, which is kind of where we got a lot of that data from. It's kind of tagging it on to other routes. Those particles are smaller than roadway particles, but at incredibly high concentration. So. But they're also emitted during daytime. From the earlier study, we could see that plume out at least, we had some measurements at 660 meters, which is much larger than the daytime plume, and you could still see a clear signal out there.
Any more questions before we close for the day? Okay, thank you, Professor Paulson, for being here.
Thank you.